Okay, so we have talked about how we can determine the shape based on the number of bonds and the unshared electrons around the central atom. Now we're going to go over this next column, which is labeled polarity. This is more complex than what we're going to talk through, but we're going to keep it simple, and we're going to give you the basics behind how you can quickly determine if a molecule is polar or not polar. Now, what does that term mean? Polarity refers to the distribution of charges around the central atom. So again, what does that mean? Well, remember that electrons are negatively charged, and we have electrons distributed around our atoms, okay? Sometimes they're paired in bonds, sometimes they're free, but we have electrons. When the distribution of electrons is equal, then we say that something is nonpolar, okay? Nonpolar means that there is an even distribution of electrons. Things that are polar, for example, the North and South Pole, they are uneven. They're at opposite ends of the continent, okay? So think of polar as your North and South poles. They're different, they're far apart. Polar atoms don't have an even distribution of electrons. And I'm going to show you in picture form how we can tell what is polar versus nonpolar. But before we get to that, notice in this third column on the table, some of them have a choice between P or NP, which is polar or nonpolar. And again, I'm going to show you how to make that decision. And then there are two shapes that are always polar, and we'll talk about why that is. All right, so let's go forward in the notes here. Okay, so polarity. First, nonpolar molecules. Nonpolar molecules are equal on all sides. And what I mean by that is all of the atoms surrounding the middle or the central atom are the same. So if we were to put a pin in the middle of this, in the middle of B, we would look around the outside and see that all of the atoms on the outside are fluorine. Nothing is different, so therefore it is nonpolar. Again, we look at an atom. In this case, there is no central atom, but if we were to put a pin in the middle, which would be right in the middle of these two, we can see that the atoms on both sides are the same. Okay, so there's an equal distribution of charges, and therefore we have nonpolar. Here's another example. CH4. Put a pin in the middle of the carbon, look around it, and you got 4 of the same atom. So again, non-polar. Okay, so if all the atoms are around the outside are the same, it is non-polar. Polar molecules, on the other hand, are not the same on all sides. So the molecule is not equal on all sides. The atoms surrounding the central atom are not the same. So if we look at CH3Cl, we've now replaced one of the H's with a chlorine. That's different. So even though we have 3 hydrogens, we have a different atom. So that makes it polar. And it's pretty obvious to see that there's not an even distribution of electrons here. Okay, again, here's my middle, put a pin in it, look on both sides, they're different. So again, polar. HF is no central atom, but again, the middle's kind of here in the middle of this bond, and hydrogen and fluorine are different, so therefore it's polar. And last but not least, if we have BF2H, F, and H are different. So we've got polar. Okay, pretty basic. There's just one trick to this. So we're talking about things around the central atom being the same. And in this case, we have all atoms around the central atom. And it's very easy to see if they're the same or not. But what about a situation where some of the things around your central atom are actually electrons, free electrons? So anytime you have extra electrons around your central atom only. Okay, so you always look at the central atom just like you do for the shapes. When you have unshared or unbonded electrons, that automatically makes it polar. The reason is, even though it looks like these are the same, we also have two sets of electrons and they are not the same. Okay, so pretend those were different atoms. They are different than the hydrogens. You'll often see water drawn like the bottom picture here in a bed shape. Either one of these electron structures are the same. They both give you the same shape and they both give you the same polarity, but it's a little easier to see when it's drawn like the bottom picture why things are not the same around the outside. Okay, but all you have to do is look for those unshared pairs. I don't know why that's not there. We already did that one. Okay, so I'm just going to draw 3 quick examples on the screen. I want you to figure out if they're polar or non-polar, then I'm going to call on people to answer, and then I'm going to give you time to work. All right, so here's our first example.
Bye.
Bye, Isabella. Sorry, those are dots, not real pretty. Okay, so take a look at each of those and think about what makes something polar versus non-polar. And then I'm going to ask for your answers. All right, let's go with Zach. What about this first one? You think it's polar or non-polar?
Non-polar.
Okay, non-polar. Why do you think it's non-polar?
Because everything surrounding it is the same, and but all of the central, all the things are bonded, right?
Okay, so Zach said that both of the atoms around it are the same. Okay, and he also checked to make sure that all of the extra electrons were in bonds. Okay, there's no open electrons here. Okay, so this is in fact non-polar. Riley, how about the next one, NH3? Yep, excellent. So NH3 is polar. This one, a lot of students get wrong. The reason it is polar is because of these extra electrons. Okay, that automatically makes it polar because they are on the central atom. If you just looked at the atoms, you might think non-polar, but this screws it up right there because that's something different around the outside. Automatically polar. Okay, polar, non-polar. And let's see, Kevin, what about the last one? What do you think there?
Polar.
Polar, good. Why?
It's what you said previously, so.
Okay, we have 3 different atoms on the outside here. Okay, now these electrons on the oxygen, they don't contribute to the polarity per se. There's no extra electrons on the central atom, but the fact that we have 3 different atoms here automatically makes it polar. Okay, so now we're going to just practice a little bit. This is very short. I'm going to have you go into ClassKick while I pull up the assignment. I've got to clear that. ClassKick. Okay, the assignment is called 2-8 molecular polarity. Essentially, it's a refresher on your shapes, and then you now have to add an extra piece here. So look at your structure, use your table to figure out the shape, and then determine if it's polar or non-polar based on the examples we just did. Now, I recognize that you only have 2 possibilities here. So you could type in P, and then if it was wrong, you could type in NP. But the only way you're going to learn this is if you truly try to figure it out. So let's say I look at this and I think it's polar. Okay, I'm not going to say whether it is or not. I'm going to type the P in there. Then if it's wrong, I'm going to look back at it and try to figure out why it was wrong. Okay, that's how you have to learn.